So today's training topic is going to be all about linking Z to working distance in an SEM. And our key objective of the training video is going to be explaining the relationship between stage position, sample position, working distance, and focus. And we'll start by using an animated demonstration to explain what's happening behind the scenes in the SEM, and then we'll go through a live demonstration as well on a real SEM to show you how this will work inside the microscope itself. And our main goal here isn't to ensure safe operation of the microscope, but also to make microscope operation and image optimization easier for the users. So for our animated demonstration, we'll start with just the pole piece and the stage, and to get the ball rolling, we'll also put a sample in. Now, the four key components that we're focusing on today are stage position, sample position, working distance, and focus. And we're also going to address how they interact with each other inside the SEM. So we'll start with the stage position. Now, at Purdue University, we have all of our SEMs set up so that when you first load a sample inside the microscope, the stage will be at its absolute lowest possible position. And inside the SEM, that's read as a coordinate of 0 millimeters in the z-axis. So the z-axis is the stage height. Right now you can see that we have an upward facing arrow that indicates that we're measuring how far we've moved the stage up from its lowest possible mechanical position. Right now we haven't moved the stage, so we're at 0. As I move the stage up, that readout will also change. In this demonstration example, I've moved the stage up 54.5 millimeters, and so that's what my stage reads out. You'll also see this inside the SEM as a readout in the navigation tab, and I have a demonstration of that at the top here. You can also see that same upward facing arrow is indicated by the z-axis in the microscope software. So the important thing to note here when talking about our stage position is noting where this stage position is actually read from. So you can see in the diagram that there's a dashed line showing final stage position, and this is showing just the height of the stage. It has no information about the sample height. So that brings us into sample position. The height of the sample is initially unknown to the microscope software. The microscope system has no way of knowing whether you put something in that's 1 centimeter tall, 1 inch tall, or much taller. So knowing that sample height is very important for the safety of the microscope and for optimization of parameters inside the microscope. And the main point here is that we don't know the distance between the pole piece and the sample. And that's important for both parameter optimization and safety of the microscope. For example, if I put in a sample that's quite tall, I can make a small movement in the stage position that's actually quite dangerous to the microscope. So for example here I'm starting at 54.5 millimeters, and we can see that there's only a small gap between the sample and the pole piece. The microscope doesn't see that right now. All it sees is this large gap between the stage and the pole piece. So if I request a relatively small change to go from 54.5 millimeters up to 60 millimeters, the microscope thinks that's perfectly safe. But what actually happens in reality is I run into the pole piece with my sample, and I break things. You can break the pole piece, you can break your sample, and this leads to lots of problems really. You're not happy, we're not happy. We have a broken microscope. Other users aren't happy because now they can't use this microscope until it's repaired. We did have this happen at Purdue University once. We had a student run their sample into the pole piece and they did break it, and this cost us about $30,000 to get that repaired. So it is a big deal, and it is important that we prevent this sort of damage to microscopes in the university. So let's not focus on that. We're going to instead focus on how to do this correctly so that we don't have any problems and we can keep your samples and our microscope safe. So the key question here really is, how do we find out the distance between the pole piece and the sample? And we're going to do that using the electron beam itself. So when I add an electron beam to my diagram here, I'm going to show it just as two lines that have a cross point. And in reality, this whole area demonstrated by these two lines is filled with electrons. For the sake of the animation being simpler and the diagram looking simpler, we're going to just represent it by these two lines, but just understand that the area inside those two lines is actually full of electrons. So the electron beam itself does have a focal point where the electrons come into focus, and that happens at this crossover point between these two lines. And how we measure that is with working distance. So this is telling you the working distance or the focal point of the beam. And as we change the focus knob on an SEM, that working distance is going to change. As we look at SEM images inside the microscope, because that focal point of the electron beam does not line up with my sample, I don't get a very in-focused image. Where the electrons actually reach the sample, the beam is quite broad, and so I get a very blurry image as demonstrated in this SEM image in the top right. Now that working distance is always recorded in the SEM. It's in the data bar of this SEM image. I'm going to blow it up for the purposes of making it more obvious during the demonstration. But as I change my focus knob inside the SEM, I'm going to be changing the working distance or the focal point of that electron beam. And as I get to 5 millimeters working distance, I'm a little bit closer to my sample. The image is very blurry still, so it's not quite good enough. But the important thing to notice here is as I change that focus up and down from 3 millimeters to 5 millimeters, the sample doesn't move and the stage doesn't move. So you can see my stage position is not changing. As I start to get closer to my being in focus, you can see that I can start to see some detail in the SEM image. It's not perfect, but I can start to make out some features of the sample. I'm still at 9 millimeters working distance. You can see in the diagram that the focal point of the beam still does not quite reach the sample. So that's why my image is not quite in focus yet. But as I continue adjusting my working distance, what we're looking for in the SEM image is a nice, clear, crisp, in-focus image. And when we use that phrase in focus, what we really mean is that the working distance of the electron beam coincides with the sample surface. And you'll see that we have good resolution, good image quality, we have nice sharp features in our image. Now this is how we determine where our sample is inside the SEM. So when I have my sample in focus, I can do something called linking Z to working distance, and that's really what we want to focus on today during this training video. And what happens when I link my Z to working distance is when I click that button, what I'm really doing is taking that working distance, so the working distance of the electron beam, and I'm transferring that value to my Z-axis of my stage. So you can see that it also changed up here in my navigation tab of my SEM. And the important thing here is that we've changed the direction of our measurement. So what's actually happened inside the SEM, if I go back to my diagram here, is I've changed where that measurement comes from. So now I'm measuring the distance between the pole piece and the sample. And so inside the Z-axis inside the navigation tab, you can now see that the directional arrow showing you where that number is coming from has changed from pointing from the bottom up to pointing from the top down. And this shows us that we've changed where that measurement is happening. The reason this is helpful for us is now that our working distance and our stage position are linked, now we can actually type in values for stage position, and when we hit enter, it's going to move the stage so that the sample is in the position that we asked for. So you'll notice that my stage has now lowered so that my sample position is 10 millimeters away from the pole piece. And so this linking Z to working distance actually coordinates the stage movements to the sample position. You should also notice that when we've linked the working distance and the Z-axis, we also see that the working distance has automatically changed when we moved the sample position. So my working distance automatically moved from that 9.7 to 10.0, and that means that my SEM image has stayed in focus during that stage movement. So that's an added benefit to linking your working distance to your stage. Whenever you make stage movements, the microscope will do its best to automatically refocus that image for you by changing the working distance as well. Alright, so I also want to cover what happens if you do this wrong, because that emphasizes why this is important. So, to take an example, if I've changed my focus knob on my microscope so that my working distance is 14 millimeters, but that's not actually lined up with my sample. You can see in my SEM image that I have a blurry image. And so if I link right now, I'm feeding the microscope incorrect information. You should only click link Z to working distance when your sample is in focus. But if I do it when I have an out of focus image, the microscope will believe me, it will listen. And so it trusts me and says, okay, I've changed my stage position to be 14 millimeters. It reads that distance now between the pole piece and the sample as 14 millimeters instead of the correct value of 10 millimeters. And where we have danger here is I can now tell the microscope, please take the sample to 3 millimeters working distance. I want to move my sample to be 3 millimeters away from the pole piece. But because I've linked incorrectly, when I hit go, it tries to listen to me. And again, we've hit now the pole piece with our sample. We go back to $30,000 worth of damage. The microscope is not operational until we can have a service engineer come in and swap the parts, have the parts shipped to us. So again, this is why linking is so important inside an SEM. So now at this point we're going to move on to our live demonstration so you can see how this will look inside an SEM on Purdue's campus. For our live demonstration, we've just loaded a sample into the Aprio SEM that we have in Whistler at Purdue. So I'm just going to go ahead and pump the chamber. And while the system pumps to high vacuum, I have control to change the height of the stage. So going back to our animated video, this is going to be changing the stage position. So in the right-hand side here in this software, we can get to the navigation tab on the right. And when I click on that, you'll see that my Z-axis does have that upward-facing arrow that we saw earlier in the animated demonstration. When I look at my CCD camera, I can see the position of the stage inside the microscope chamber. So if I click the mouse wheel like it's a button, that's going to draw a line on my CCD camera image. And as I drag my mouse upwards, still holding that mouse wheel as a button, I can start to move my stage up. And you can see in the top right corner in that navigation pane, my Z-axis is updating as we speak. So again, at this point, the microscope has no information about how tall my sample is. The only input it has is the position of the stage itself. So I'm just going to keep driving this sample up until the surface of my sample is about at that 10 millimeter mark. And it doesn't have to be perfect. The only goal here is to have an approximate idea how far away my sample is from my pole piece. And the main reason I do that is it will make focusing easier. Remember from our animated version of this demonstration that when I change my focus knob, it changes the working distance of my electron beam. So if I already know that my sample is approximately 10 millimeters away, that just makes it simpler for me to optimize my working distance to get an in-focus image, because if I'm working with a working distance of 50 millimeters, I know that I'm nowhere close to my actual focus point. So my samples chamber has just now finished pumping to high vacuum, so I can come up here to beam control and turn the electron beam on. Now if you were sitting at the microscope, you would hear that valve opening. I'm doing this demonstration from my computer remotely, so you can't actually hear any of the microscope clicks. But I'm going to highlight my electron image in the top left quadrant here and unpause that. And I'll just do a quick auto brightness and contrast here as well, so I can see something. So when I look at this image, I'm going to speed up my dwell time really quickly here, so my refresh rate becomes a little bit quicker. You can see that I have a blurry image. So again, if I link right now with an out-of-focused image, this is where we run into issues of having incorrect information fed to the microscope. So before I click link, I'm going to bring my image into focus. All right. And when you're using the SEM, you do have the option to use a reduced area tool to do fine surface detail focusing so you get a better resolution in your image, because I'm updating fewer pixels here, so I can use higher pixel dwell time and higher scanning resolution. You can also hit F5, function key 5 on your keyboard so that you can see a little bit better. And there, my image is in focus. All right. So now that my image is in focus, I can take a look at my working distance here and see that the electron beam is actually focused at a working distance of 11.1 millimeters. And if I pay close attention to my CCD camera, I can see that that makes logical sense. My sample, if I make this window full screen, is actually a little bit lower than that 10 millimeter working distance. So all of this makes sense together. Once I know that my image is in focus, I'm focused on my sample, I can highlight my electron window again, and then click this Link Z to FWD button. Just before I do that, I'm going to show my navigation tab again because I want you to see this Z-axis change. When I click Link, it will tell me what I'm doing and why I'm doing it. It reminds you here the system cannot recognize the height of your specimen. To define the minimum Z stage position well, please focus on the highest specimen surface. And we have focused on the tallest point of our sample, so that's okay. We'll go ahead and hit Link. And now my working distance value has been transferred to my Z-axis position. And from here, I can now type in 10 millimeters as my desired sample position. And when I hit Enter, you can see it moves my stage and it refocused my image for me. Okay, so that's the basics. I'm also going to show you how this will work if we didn't have the CCD camera here. So I'm just going to move us to a much lower stage position here, in this case 60 millimeters, because in reality it's possible to do this without a CCD camera. The CCD camera is there to help you. It's not actually necessary in order to do the linking. So as my stage drops here, if I imagine that I've loaded my sample, I've just now pumped the specimen chamber, and now I'm just now trying to find my image. Initially, my working distance would be at 10 millimeters working distance. And I can change this and type in a value. Right now, because I've actually already linked, I know that my sample is all the way down at 60 millimeters. But if I didn't know that, I could just change my focus and say, that's still blurry, that's still blurry, it's terrible, it's terrible, it's terrible. And it will take me quite a long time to get that image into focus because I have no idea where it is. So that's where the 10 millimeter mark is just a helpful reference. But as I do get closer to that 60 millimeters where I know the sample is, you can see I'm at 40 millimeters working distance and getting longer. So I'm starting to see some features in my SEM image. They're still quite blurry, but they're coming into focus. And I can actually make this full screen because I'm ignoring my CCD camera right now. And here we are. And you can see that if I can find my sample and focus on it, I don't actually need to see the CCD camera. I can link my stage and then know exactly where my sample is. So I'll just turn on my reduced area tool here, get my image focused, and I can see that I have some astigmatism in this image, so I'll correct that too. Alright. There's my crisp in-focused image again. That means my electron beam is focused on my sample, so the working distance lines up with the sample surface. And so now I can go ahead and link the stage. It tells me now that it's already linked, but you'll also see in my working distance that I'm now focused at 60.6 millimeters, not 60.0. So another thing to keep in mind that the stage is not perfect in terms of mechanical movements. When I've made a very large stage movement from 10 millimeters to 60 millimeters, it's not perfectly accurate. So this is where you can relink anytime as well. If your focal point has changed, your sample has moved, I can click this link Z to FWD just to update and have a more accurate value for my Z-axis. And then, without being able to see a CCD camera, I can drive my sample up to 10 millimeters safely. If the CCD camera is not available, you also need to know something about your sample ahead of time. So if you have a very uneven sample that has significant height differences across the sample, if you focused on a low point in the sample, a short feature, and then linked the stage and drove up to 10 millimeters, if your sample is taller than 10 millimeters in other portions of the sample, then you can still make contact with the pole piece or other detectors inside the microscope. So this is best when your sample is reasonably flat. The CCD camera is there to help with uneven samples, so it is a helpful tool. You should use it. This portion of the demonstration is basically to show you linking can substitute for a CCD camera, for example, if it's broken, or if you happen to be working on a microscope that's old enough that a CCD camera simply isn't present in the microscope. And again, you can see that because the mechanical movement of the stage is not perfectly accurate, I'm not quite in focus again. So we'll just refocus. And then I can link again. And now that my linking is more accurate and I'm making smaller stage movements, I can move the stage again. And the image does refocus for me. Alright, that concludes our linking Z to focus working distance video. If you have any questions, as always, please come and ask a member of staff. We're always happy to talk to you guys, and hopefully we'll see you using the microscope soon.